So, good morning, everybody. I would like to officially welcome you to this new training session, RICAIP training, entitled Automated Assembly BIM Picking System for Cluttered Environments with Live Collision-Free Trajectory Planning. This training is one in a session of trainings we have offered before. If you have assisted before to these kind of trainings, you must have seen my colleague May and her previous work, and today she's joining us and taking the time to report about the advancement she has been working on lately. So May, if you're ready, I guess we can start.
Okay, thank you, Kenza. I will start my presentation now. Hello, everybody. Good morning. Welcome to the presentation, Automated Assemblies Picking System for Cluttered Environments with the Live Collision-Free Trajectory Planning. Today, I will present an automatic Lego assembly systems that generates a feasible sequence and executes them via collision-free trajectory planning. The robotic arm locates the brakes in the cluttered spins and using the live point cloud data in here. In the agenda, I will begin by presenting the problem state of the assembly picking system, the research objectives, and the detailed explanations of our proposed approach. To provide the context, I will first give an overview of automate assembly picking system, helping free the scopes of this work. In dataset preparation, I will demonstrate how we compute the side distance rate of the freeform objects using the fast sweeping algorithms. The side distance rate data enables the previous collision detection within our physics-based simulation tool. Our approach integrates ASAP. This is automatical sequence planning for complex robotic assemblies with physical feasibilities. It was developed by the MIT. The planner search for feasible disassembly sequence and reverse them to generate the optimal assembly sequence. Based on the assembly sequence, we perform object detection and high precision 3D pose estimation in cluttered spin. The camera system identifies the start pose and the target pose from the sequence planner. A key challenge is planning collision-free trajectories in dynamic reconfigurable environments where obstacles may be add, move, or remove. We will present the results assessing object detections and 3D pose estimation accuracy and dynamic collisions analyze across 10 written trajectory planners, motion validations, ensuring the robot arm closely follows the intended trajectory. A video demonstration of the Lego assemblies use case will be illustrates the systems in action following the discussions of ASAP's limitation. Finally, after summarizing our finding, I will conclude a live demo of the system. The assembly pickings consist of our problem. It is because our automatically the assembly sequence it will be in the very chaotic environment because I don't know where I pick and where I place. And my product each time I also don't know. So this is a challenge for us when I don't know where I start and end, and also where is my environment. So in this assembly picking systems, we will try to solve this problem that give the robot inputs is the CD for a general product, and then outputs it is the robot assembly dance and give to me. So that means the robot should think about based on the CD model for the complete assembly, try to find the sequence first. And then based on the sequence plan, it will identify the breaks or the parts in the cluttered environment. And then it will try to make the object detection and 3D pose estimation to define the star pose from the trajectory. And then the place position will be defined from the sequence where to place. So the trajectory plan is try to help the robot make a collision free and then smooth it to pick the parts and then to assemble it. So my approach will be integrate the ASAP assembly planner into my bin picking systems, and then I will improve the object detections with the traditional house sorting with the global registration method to identify clear the object in a very cluttered environment with the 1.5 million point cloud. And then it will doing the service refinement, use the best fit to make the very high accuracy, 1 to 2 millimeter post estimation. And then CD is try to help to make the 3D post estimation more accuracy. And finally doing the collision-free robotic parts planning to finish the assembly. So here is the overview of about the assembly picking system. The assembly picking system consists of the sequence plan, the 3D camera, data management, simulations, and control system. The inputs consist of the 3D models of the Lego assembly containing the point cloud of each individual part along their relative position and all defined with respect to a base part. And 3D camera capture the live process data of the chaotic Lego brick, detect the objects and make the 3D pose estimation. 3D cameras will send the 3D the gripping pose, 3D the bin pose, and the real point cloud mesh to data management. Data management will store the robots and the environment properties in the assets administration shell. It will check the changes in environment properties and send the CAD mode, the 3D gripping and assembly pose, real point cloud mesh, and 3D bin pose to the simulation tool. Simulation tool builds a virtual environment like the real ones and returns a collision-free trajectory of the simulation. If the simulation check there is no collisions, the data management is sent to the control system to implement the robot arms and the real environment. The point cloud data of each component will be processed to compute its corresponding side distance frame. Why is it important? Because side distance frame is to help to detect collisions in physical simulations, help the sequence to check about the structure stability. As implicit surface representations capable of the modeling arbitrary geometries, a side distance frame defines a scalar phrase where each point in space stores its shortest distance to the object's surface. The distance matrix carries side information. Negative values indicate interior points, while the positive values denote exterior points. Among fast sweeping methods, three principal variants are particular significance theory analysis. Uh, and theoretical analysis demonstrated that for 3D free-form objects, the method guarantees convergence within a maximum of the A sweeping across all 3 dimensions, just like the video. The core concept of the fast sweeping method lies in utilizing the monotonicity properties of the partial differential equation. It iteratively sweeps through grid points in alternative direction, progressively updates values at each node until convergence criterions are met. The individual iteration look for the unique solution for a quadratic equation. These 3 equation will be very important to the fast sweeping method. You don't need to drive with the complex mathematical proof from the original paper to use the fast sweeping method. Let me explain with a straightforward 2D example. First, imagine our source point represents the boundary of freeform object. The algorithms initialize neighboring points with huge values. Theory called infinite. In 2D space, we will need 4 directional sweeps from each corner of the square to guarantee convergence. This extends locally to 3D space where we will sweep from all 8 corners of a cube. The algorithms will begin by update the variables at position T10, T2, T12 and T21, and T22 using the 3 kits formula, but only when neighboring values are infinite neighboring, providing the updates. As the sweeping process, subsequent updates affect T13 and T23, while T33 remains unchanged, still T32 is still infinite. The third sweep propagates updates through the third row's values. By the fourth iteration, convergence is achieved as all the values have reached their minimal possible values require no further update. The generator is shown in here with the point cloud customized feature encoder and the graphene neural network and this multi-layer perception classifier. The generator will receive the components and determines the Lego assembly order. ASAP's the learning-based generator will process this data through the 4 model before recommending which break to remove. ASAP employs a learning-based graphene neural network to optimize the tree search process. Also, it's not our original contribution. I will provide explanation of the network architecture for clarity. It has 4 module. PointNet encoder is to try to use geometry feature from the point cloud, and the customized feature encoder is part specific data like volume, distance, center of mass, and so on. So it try to handle the information. And the graphene neural network message passing layer and the multi-layer perceptions classifier. The encoder creates initial graphene nodes embeddings updates via 2 messages passing rounds. The multi-layer perceptions that predict the next part to disassembly. For training, ASAP employs a standard binary cross entropy loss to supervise the model, comparing the predicted probabilities of the disassemblies given parts against the grand truth label, which indicates the correct next part in the sequence. When the generator decides the next disassembly part, the physical simulation tool will check the assembly. So the ASAP sequence planner is based on a disassembly and assembly principle. That means for a redundant assembly, you try to, in the physics simulation, based on this iteration to remove the part. That means you will disassembly the part first. If you can find the disassembly sequence, so it will try to reverse the assembly and then try to find the sequence. A constants here will show how it will check about the assemblability. A constant translation force is applied to the assembly's object from state S using one of 6 degrees of freedom action. In physics simulation type delta t, each action is applied continuously to state S until the resulting state S either disassemblies or match a parts state. If the disassemblies the part from S0 to S is retrieved via tree backtracking, suppose the resulting state S resembles a parallel state, measures by translational distance smaller than a tracehold. In that case, the action stops. The resulting state S is unclear, and the search continues with the remaining actions. Constraints movements, for example, tight space, limits the sample-based motion planning as it's often failed to find collision-free parts. This assembly succeeds if translational force works in any of the 6 possible direction. In the video, it just show one of the part how in physical simulation you try to give the force in one of the degree of freedom to move it. If this part can be moved in just one of the degree of freedom, that's the sequence will think, okay, it can be disassembly. So the assembly check will be true. Now let's go to the stability check. Stability check, it is when, for example, when I remove the part number 9, so I will check about the whole structure. Is it stable or not? When identify a removable Lego brick, the structure stability of the remaining assembly must be maintained. Next, the ASAP sequence planning performs a physical simulation for up to n steps to evaluate stability. At each step, ASAP sequence planner checks the update position of each part and compute its Euclidean distance of the initial position. If this distance exceeds the threshold, parts marked as unstable falling. Additionally, ASAP check whether parts lose contact with the adjacent part, another indicator of instabilities. Unstable parts are apt to list P, tracking restart of the process. The algorithm terminals when either a visible list P is identified or the parts limit is exists. Notable, we use the positional displacement rather than velocities or accelerations for stability assessments due to it is temporal smoothness in contact-rich simulation. In here, I show an example. For example, the sequence plan will check about the parts 4 until 8, the movement in 1,000 steps, and then to see if each of the part is a move out of 0.2 millimeter. If it's move out of 0.2 millimeter, that the stability check will say, okay, the whole structure is not stable. I didn't check about 0 to 3 because 0 to 3 is my base part. It's already fixed in the simulation, so I didn't need to check them. The ASAP sequence planner can only identify the assembly's sequence for a small number of simple parts among the test Lego assemblies, as shown in the left figures. When Lego bricks A is assembled, Lego brick B is easily found because it is not fully secured on the Lego brick C. To address this, we need to enlarge the circular nose of the Lego brick C to improve grip when brick A is removed. The middle figure highlights a key limitation of the original ASAP planner, which only fits a single brick at a time. In contrast, our upgrade version simultaneously address the multiple brick to ensure that the parts on the base are remaining stable when upper sections are removed. Finally, the right figures illustrates another issue. The ASAP sequence planner sometimes generates ASAP sequence that cannot be physically executed by the robot's arm. To resolve this, we must refine the collision detection criterion to ensure the feasible sequence that follow the button-up assembly approach. The next slide, I will show the video how the assemblies to generalize. In this video, we demonstrate how the sequence plan validates various Lego assembly with different parts. There should be different parts for each of the variants. Here is speaking about the 3D camera system. After the sequence plan, find the sequence. Here it is the workflow of the self-developed object detection and hand-eye calibrator and application interface. In this research work, we need to build a Vision Pro project. The Vision Pro project consists of an acquisition tool and a self-developed detection tool. The acquisition tool gets a point cloud image from the camera or the fire, and 3D HMS is using to train the feature of the Lego brick to recognize the Lego bricks in different size of new image. This is what we are doing before in step 2, but now we have our self-developed object detection tool, so it will show detail in the later. And the first step is to explore the point cloud view based on the point cloud of the Lego brick surface. And the application interface has an acquisition tray to receive the image and an image processing tray to extract the region of the interest of the self-developed detection tool. The point cloud in the region of the interesting is considered the point cloud of the Lego brick surface. A tailored best fits method to process the point cloud and determine the object's orientation. The processing result matching the 3D model and gets the gripping pose based on the camera coordinate system. Transformation of the gripping pose to the robot coordinate requires the calibration matrix from the camera coordinate to the robot base coordinate. This is the overflow. Here I show very detailed how I do the object detection. In cluttered environments, the objects are very in size and readily positioned, densely packed within bins. The model point cloud represents the target objects can be detected. For example, the green point cloud of the median Lego bricks, typically containing 3,000, 4,000 points. The sense point cloud captured by a 3D camera, it covers the entire bin and can range from 1.5 to 2 million points. traditional method, like the house workings method, struggles with the effective registration due to the waste scale difference between model and sense point cloud. Our self-developed detection tool overcomes this challenge through the following steps. Feature points with extractations. Both point cloud and both model and sense point cloud are analyzed to identify the feature points, the key points that will capture the critical geometry information. For example, the point on the corner, edge, and planar surface. Each feature point generates a local reference frame based on its neighboring points, ensure rotation invariance in later computation. Correspondent matching as shown in the figure. Feature points in the model point cloud are computed relative to the model's center using the LRF coordinate system. These feature points then attempt to form corresponding pairs with matching feature points in the sense point cloud. In real-world scenarios, since the noise of the point cloud significantly reduced the percentage of the correct correspondence pairs, often less than 5%. As illustrates the figures, the green dot light represents the correct correspondence pair. The red dot light indicates incorrect matches. Using these corresponding relationships, we will determine the central points of the sense point cloud relative to the camera coordinates instance as defined by the equation. Notably, the two correct corresponding pairs will produce identical values. When applied to point cloud with the numerous feature points, a key observation emerge the values derived from the correct correspondence cluster together in 3D space. Will be seen in this feature. To analyze this, we partitioned the sense point cloud into small 3D cubes or versals. The endpoints of each vector calculated from feature points and their corresponding vector will fall within one of these versals. Each versal functions as a working beam, where each arrow and positions case a void. The versal receives the highest number of the voids indicates the most probable object location. See the figure, like the arrow in here. We then apply a voice threshold to identify the sense point cloud regions that match the reference point model's feature. However, traditional working-based detection face limitation due to sense scale, complexities, and noise. These factors often lead to false identification and misalignment errors. These challenges are particularly pronounced when detect objects like Lego bricks that have similar surface feature across different pieces and significant size variance between components. The sensor median point noise data results exceptional lower correct pair rates, leading to registrations failings and imprecise 3D localization. To address this, we improve upon a global registration method shown in the features step C to D to stabilize the cluttered environments and correct post-estimation errors inherent in house workings approach. Our primary innovations will achieve this reliable detection of the various objects, including challenge reflective methods This pad substantial scale variance and high noise cluttered condition. We'll see in the figure step F. And then we'll get a very clean Lego brick surface point cloud. The global registration method process two inputs. The model's point cloud, we call it source point cloud, and then the chop sensed point cloud, we call it target point cloud. The algorithms process through these key steps. Initial feature matching, like the A, the fast point feature history descriptor establish a preliminary correspondence pair between source and target point cloud. And noise robust featuring is on the step B. Translation and rotation invariant measurement are computed from the initial pairs. A noise bonds constraint feature outliers, retaining only geometry consistent inliers. Optimal correspondence selection is from C to E. The maximum click-quit algorithms identifies the most interconnect points at the optimal reference. This selection use the largest sets of mutually consistent inliers. Precise post-estimation is from F to G. Rotation is estimation through best fit matrix computation using maximum click-quit inliers. Translations vector are determined via an adaptive working mechanism. And then finally, is trying to from the house working the result, and then try to match this green point cloud very perfectly on a Lego brick surface in the sense point cloud, and then trying to get a clean surface point cloud, and then to do the next step, the 3D post estimation. So under this road, it will show the different example in the object detection. The goal of the best fit method is to extract a point cloud of the surface without circular nodes. Another goal is to define the accurate position and orientation of the gripping post based on the camera coordinate system. The first step is to preserve the surface point cloud inclusive nodes of the area of interest will be slightly larger than the actual size of the Lego brick. The second step is to preserve the surface point cloud exclusive of the nodes of the area of the interest with the actual size of the Lego brick. It will repeat the processing step 2 to extract more accurate surface point cloud. The last part shows the processing result. On the right side, it will show detail how the best fit method work. We given all the surface point cloud in 3D and calculate the mean values to set up the matrix A as the equation. Minimize the error R via single value decomposition to determine the normal vector N based on the camera coordinate system when matrix V is multiplied by Z vector. The vector aligned with the long side of the Lego brick P can be obtained when matrix V is multiplied by X vector. The vector C is from the vector N cross product with the vector P. Vector P, C, N are defined as the X, Y, Z axis of the Lego brick. They are unit vector. With them, we can write the rotation matrix like the equation and get the transformation matrix. Based on the position and orientation, we define the area of interest and preserve the point cloud inside the bounding box. This here will show how the CD point cloud automatically matching with the Lego point cloud from the 3D camera using ICP. Partially occurred parts can use the CD point cloud matching to estimate the 3D pose. The original is the CD point cloud, core source point cloud will be drawn in the SolidWorks and convert to a point cloud. Green is the CD point cloud after the best fit method fits into the Lego point cloud. Inputs to the ICP are green point cloud, blue point cloud, and the unit identity matrix, and the output is the transformation matrix from green point cloud to the blue point cloud. The best methods calculate the transformation matrix of CAD point cloud to camera coordinate system. With best fit method, the transformation of the Lego point cloud based on the camera coordinate system will be also calculated. We need to decenter the CAD point cloud to the point cloud center of mass and place the CAD point cloud in the Lego coordinate system. Calculate the CAD point cloud in the camera coordinate system, specifically the green point cloud. The central coordinate defined by CD are shown in the formula. The input to ICP is the blue point cloud, green point cloud, and identity matrix. So the outputs from the ICP is a transformation matrix from the near target point cloud based on the Lego coordinate system. With the ICP, we can obtain the TCP relative to the camera coordinate system and transfer by the hand-eye calibration matrix, we can obtain the CD in a robot-based coordinate system. Here show detail how we do the hand-eye calibration. Hand-eye calibration aims to obtain the transformation from camera coordinate system to robot-based coordinate system. The calibration targets will be mounted in the robots and move with a tilt angle around 5 to 20 degrees. At least 5 clean point cloud images are required, and the correct robots from the teach panels. Because the camera has a large working volume, it needs to train calibration target from the first point cloud image. The another point cloud based on the train patterns detects the calibration targets automatically. The eighth point of the target should not be obscured. The camera coordinate systems from the best fits and CD matching method transfer to the robot coordinate system will show in here. From the previous introduced method, we can get the Lego brick based on the camera coordinate system. And BDC is our hand-eye calibration system. With this transformation matrix, we can get a gripping pose based on the robot-based coordinate. We train the Lego brick just one time to obtain the transformation matrix from 2 center points to Lego brick center. The robot with the measuring tip moves to the center of Lego brick 1 and gets the TCP/TB in the equation. We calculate the transformation matrix from the Lego brick center to the 2 center points. When we have the new Lego brick, we can use the last equation to calculate. So here it is because the center from the Lego brick defined from the camera coordinate sensor will have some systematic error for the real one. So we are doing this step just one time in order to get this transformation matrix from the 2 center point and then to the real robot center point. Here it will details to show how a collision-free trajectory will be planned. When we define the start pose, after determining the camera and sequence plan's start and end points, the path planner constructs a search path. Search points will give the planner a direction to find a path. The starting point is checked for collisions. A k-dimensional tree generates 7 random points in the 3D space and determines a temporary point. Intermediate points are interpolated from the start points to the temporary point. If intermediate points and temporary points are collision-free, the temporary point is designated as the next. The loop repeats until the endpoint is reached. After defining the start pose of the 3D camera systems in the cluttered environments, the end pose from the sequence plan, a collision-free trajectory will be planned. Sorry. Here we'll show how to will show detail how the trajectory planner will try to find the nest. The trajectory planner will proceed from the start pose to the end pose. In this slide, I will demonstrate an example how the search from the next waypoint n+1 starting from waypoint n. Starting from waypoint n in the system construct a k-dimensional tree within a confined search space. The size of the space can be adjusted to prioritize either faster collisions-free trajectory planning or more through search. Each path planner iteration creates a cube space central on the allowable waypoints, starting with the initial points at the center. Several random points are generated around it. The space is divided along the x, y, and z axes. First, the median x axis is chosen from the x plate plan, and then with the median point as the root. The point below the median go to the left child group. Those above go to the right. The y-axis medians in the left group create the left y split plan, and the z-axis from the z-split plan. The same process applied to the right group. The sort k-dimensional tree divides the space into A sections. Identify the nearest neighbor as a temporary valid waypoint. Path planning explains in 3D space, divides into A subspace along X, Y, and Z axis. For faster collision-free planning in industrial reconfigurable environments, 3D dimension balance the computation time and complexity. The path planning is active to define the start and end point within the workspace. The collision check treats each complex structure modeled as a based geometry shape to simplify the environment. Special modules such like the bin I will define in the workspace with blue and yellow frames. If a planar points, it is outside the yellow but within the blue frame, is called with the bin's housing. The interpolation process splits the distance between the start and temporary waypoints into 5 equal segments. Environmental collisions are through assessed at each original point. Once the path planning determines a route, it interpolates allowable waypoints from the start to the end. A digital twin tool performs a dynamic collision track, providing minimal collision depth and penetration vector. The robot calculates collision-free paths by combining simplified and precise geometry. After planning, the robotic arm simulates the path in the digital twin tool, displaying collision data if issues arise. Figure shows the digital twin highlights the collision pair, depth, and vector, which adjusts the waypoints opposite the penetration vector to ensure the collision-free path. The temporary waypoint is valid during motion checks if the 5 intervals don't overlap. The path planning saves it. Starting from this waypoint, the next neighbor is found using the same 4 steps process until the waypoint endpoint distance is within the KD tree range. If a collision occurs, the last valid intervals point replace the temporary waypoint, ensure the path planner process towards the endpoint. When all the robot parts related to the TCP are determined, the configuration planner focuses on the robot configuration. Here is an example of how the robot configuration will be planned from an initial pose to the first waypoint. With the backwards kinematic, we can find a maxima of the A robot's configuration. I compare the sum of the drawn variables change across A robot's configurations. I take the configuration with the minimal drawn variable change as my robot configuration and proceed with the planning. After the first waypoint, robot configuration is determined, and then based on it, the configuration planner will be continuously planned. Here we'll show the waypoint n to waypoint n+1. We benchmark the industrial 3D cameras in reconfigurable setups using Lego bricks, metal parts, and Raspberry Pi cover and operation tools. Unlike the existing cluttered picking benchmark, which poorly reflects real industrial bin picking, our method reliably detects the industrial items, also similar geometry. For example, the pie covers pose challenge to a cluttered sense. Street conditions reduce the error, but drastically cut detectable items. Commercial tool dropped from the high to few detection. Thence the metal parts lose more than 50% of the point cloud data under poor lighting and reflection. Picometers resolution camera are needed for precising tools, but higher resolution shrinks working space, a trait of requiring the project-specific optimization. We evaluate the result between commercial tool, best fit metal, and best fit metal with ICP metal. The absolute translation error diagram shows that the best fit metal with ICP estimates the pose more accurately, mostly around 1 and 2 millimeter. The orientation errors are concentrated within 0 to 2 degrees. But if the point cloud is defective in a significant area, it will influence the best fit metal with the ICP metal. In the simulation, one can simulate the robot parts and display the collision pairs, penetration vector, depth, and collision contour. Based on this information, I can avoid collisions. In the simulation, another can also calculate the deviation between the desired and actual robot parts. I take a 10 random experiments and show the dynamic collision reports. Most robot parts have a maximum collision depth of 2.5 millimeter because the gripper grabs the component. They are components in very tight positions, hence the collision occurs. The deviation between the desired and actual robot parts remain below 1 millimeter. Due to the change tilt angle of the component, the robot arm only experiences a shaky movement at the beginning. In the future, the robot part will be smoother. Finally, show the video with the Lego assembly use cases. Just make a conclusion for this section. Um, Here we'll show the sequence plan and then give to the camera system with sequence and camera try to detect it and then to make the pose estimation and then define the start pose of the trajectory and then the data management save everything and then manage the information to the simulation to build a virtual environment like the real one, try to find the collision trajectory plan. And then when everything is fine, we will send back the trajectory and then to implement the robot on. Here is show the object detection and 3D pose estimation. Here is my digital twin. I use the Siemens process simulate to with the live point cloud data. And then when everything is fine, it will send to the robot to implement. After this video and after one slide about the conclusion, I and my student will show the live demo. I just speed up the rest of the Lego brick, show very detailed for the first Lego brick in the video about the whole pipeline from the camera, from the sequence plan, from the trajectory plan. Okay, now we are going to the conclusion. Oh, sorry, I forget. Here it is the limitation about the sequence plan. So the MIT is not available to solve the problem such as when the object is solved, such as the close or gloomy something. Because in the physics simulation, when calculate this everything in real, it will be very hard. Another thing it is when my action sequence is too complicated, just like this example, that it can also not be solved because we give a force and then to see if this assembly or not. Today we represent automatically Lego assembly systems that generate the feasible simulation and executes that via collision-free motion planning. The robotic arm locates bricks in cluttered bin using real-time data guidance. Key advantages are automatically sequence generation for arbitrary assemblies, industrial adaptability via efficient detection, millimeter accuracy with outperforming optimization methods in noise environments, and digital twin enable flexible planning. limitation includes challenge button to top robotic assembly, detection degradations from mesoly reflections, suboptimal post-estimation for featureless components, unsuitability for precision applications require smooth trajectories. Future world, we will enhance the planner using affordable 3D camera and then solve the limitation problem. So now I think for example, I think some of you may see that I have some camera open now for my use cases. You can choose such as the camera with different view and then to see about that. Until now, is there anything problem from the presentation? If there's no, I and my student Jen will begin to show the live demo. Yeah. So here now is the program. Now we just start the program. Because the sequence plan needs if we choose, we just choose number 3 to show demo in live. And then after we choose it, here it is the sequence plan already file sequence for this assembly. So it just directly to send this sequence to the 3D camera. If there is the assembly that does not have any sequence, so it will try to begin to find the sequence first and then to send to the camera. But today, because of my time, don't have too much time to show very detailed about how the sequence plan file a sequence for unknown assembly. So I just start with a sequence that's for the Lego assembly in order I can show the whole pipeline of my assembly picking system. Now the camera is trying to take a picture from the cluttered bin and then try to handle the 1.5 million points. I have a lot of point cloud, but my PC is a little bit slow, so we just take a little bit time and then to wait for the camera to detect the part. Now the camera say it detect 5 large Lego brick. When it detect and then it's doing the 3D pose estimation now, so it will automatically have uh, to visualize the detect result from the robot. We need to wait for several seconds. Okay, now, so the camera give us the result. Now, Jen will try to turn around this part. You see the gray is the point cloud from my sensor point cloud, and from the side, we can see actually the BSFI and ICP method is define the part very clearly. And then the camera will tell to the data management, give the star pose. Now the data management is send everything in real, the live point cloud to the digital twin tool. Now is with the collision-free trajectory parts, and it will simulate one time to check to make sure there's no collision. So now, Jen, can you choose the smooth part? Actually, we solved the problem about the smoothing part. Maybe Jen can. So you can see that my yellow part is my trajectory planning. It's very chaotic a little bit. And then the green is the smoothie part to smooth my parts. And then Jen, I think you can close the simulation, and then we just send everything to the robot controller and then let the robot to move. Now the robot is moving, trying to pick. I have two camera of the view. If you want to see very detailed about how it work in the bin, you can change to the camera focus on the bin. If you want to see the overview, then you can stay in the camera to see the overview about the demo. So now the camera is a catch part, so the 3D camera cannot detect the color. So the if I add the RGB camera to detect the color, now the robot is trying to ask the RGB camera what could be the color of this brick. So if the size and the color both satisfy is exactly want from the sequence, the robot will try to assemble it. So the sequence plan is already tell to the robot where you should place the part. So the robot is trying to follow the trajectory plan, what we are doing in the simulation, and then try to assemble the first part for that. Okay, so I showed the first Lego brick very detailed. I just let my student Jen continue my process. If you have any question, you can ask now. I mean, when you do have any question now. I think my presentation is already done now.
Thank you, May, for the talk. So I guess questions are welcome now, as May just said. But as I see no hands raised, I guess I will go ahead and ask a question myself. And it's a question, I guess, that anybody who would see such a presentation would ask. Although the techniques behind and the methods that were presented are very interesting, one might ask, how applicable would such approaches be to an industrial product?
Yeah, this is a good question. Because today I showed the example with everything based on the Lego brick, and my technique have still some limitation, so I still need to improve. But I trying to make the whole systems to be a full stack solution for the assembly picking system. Until now, I think my sequence plan can be actually I have my own sequence plan, but today I just present the MIT sequence plan. The success rate to the sequence plan can be now 16% to 80% for me. I developed my own sequence plan. It's called FAST. And then the object detection and 3D pose estimation, the object detection need to define the part when the part is not very must have some feature. For example, my part should be like Raspberry Pi or Lego or some other part that's have a good geometry doesn't can be not like a soft part. For example, like a clothes. That could be hard for me to do the object detection and pose estimation. And then the tire plan is actually very stable in because it just waiting for the start and end point and then doing automatically for all the parts. So tire plan will be, I would say, more than 95% will be success. I mean, it don't have any problem about to generalization. And I think this is my answer. Is it answer your question or not?
To some extent, yes. But I'm also very interested in knowing the adaptability of this solution to objects that are more complex.
Yes.
Like Lego bricks have like a standard geometry. They have very distinguished colors, which probably makes the problem a bit more easier to solve in like sequence planning perspective. I was wondering if that would be the case for other products that might have different geometry, that might have all the same color, probably very similar colors, that where the actual assembly is a bit more complex and so on.
Yeah, I want to share my new research for the ICRA that we upload last week. This is actually my self fast sequence plan. This is for general assembly. In the video, I mean, today what I present is already a little bit old for my research. Until now, this is the research from the last week that I achieved. So here is for I use a Raspberry Pi because RICAIP the product for us is Raspberry Pi to show very detailed from the first sequence plan. And then the Raspberry Pi is in the very cluttered environment with the fan. Here just an example in the industrial. Usually the people will not put the microstrip very chaotic in the bin, but I just want to show that what we are talking in the paper that is actually true. So here it is let the robot with the faster sequence plan to uh, self-think about what could be the sequence and where is my product. I pick it, how I assembly. So let the robot automatically to think about by himself. And then I also generalize the part with another different object. And then this is my new research for the ICRA paper. Maybe I see next year if I'm luck or not to can be luck to get ICRA or not. Yeah.
Thank you very much, May.
Yeah.
If no other questions are there, I guess we can conclude this training session. Yeah, it seems like it. Thank you very much again, May, and thank you all for being here. And see you maybe in a next RICAIP training.
Okay.
Have a nice day.
Have a nice day.